Kaimanovich from University of Ottawa, who will be talking about limit distributions of branching random walks.
Okay, thank you very much. It's a great pleasure to do a talk in this seminar again, and also do it in old-fashioned style with chalk.
Maybe put the light on here.
The title of the talk is boundary convergence of measures associated with branching random walks. So let me begin with a little apology, a little justification. Why would one consider branching random walks at all? So, as I was told by the organizers, this is a group theory seminar primarily, and therefore I was asked to keep as close as possible to group theory. Okay, so let's begin with the group. Let's begin with the group. And then, well, the first argument in my apology is that, well, if we have a group, it makes sense to consider not just elements of the group, but also it makes sense to consider elements of the group algebra. And then, moreover, one can consider positive elements of the group algebra, and even moreover, one can consider normalized positive elements of the group algebra. And this is nothing else than finitely supported probability measures on the group. Okay. If we want to talk about L1 group algebra, then therefore we are allowed to talk about general probability measures on the group. Okay, so elements measures on the group. Okay, and by now I think it's already pretty common to consider measures on groups, and there is a lot of questions proper to group theory, which can be formulated and answered by using measures on groups. Okay, so that's the first point. Now, the second point is that it is also useful to consider not just our group, but in many questions it is useful to consider a certain boundary of our group. And then, okay, so for instance, one can talk about spaces of n's, which is a bit old-fashioned, or about the hyperbolic boundary, which is more modern, or various other boundaries as well. And then it also makes sense to consider measures on the boundary. One example of such measures is the class of the Patterson or Patterson-Sullivan measure. Okay, and then moreover, since by now I'm allowed to talk about measures on the group and measures on the boundary of the group, and then moreover, one can now ask the following question. Suppose that we have a certain sequence or a family of measures inside the group, on the group, and then, well, one can look at the limit of, at a limit of this family, and this will provide us with a certain boundary. So, boundary measures. As limits of internal measure. Okay, now there is one instance where this correspondence is really working with full force. And this is the class of random walk on groups. The theory of random walk on groups provides us with a very nice illustration of this principle. And here nowadays, I don't have to put any extra justification because by now I think it is acceptable even for group theory to talk about random walks on groups. Yeah. Okay, so what is the setup there? We have a group and we have a probability measure on this group. And in this situation, we can consider the so-called random walk, which is the product of independent, identically distributed increments with the same law, which is the step distribution. Now, here, what happens if you look at it from this point of view? So, this correspondence between measures inside and then measures on the boundary. Okay, so here there are two instances. The first one is that in principle, one doesn't even have to talk about random walks for this, because if we have a probability measure on the groups, then we can talk about its convolution powers. So it's one is allowed to talk about convolution powers without invoking random walks. And then, if we are talking about groups endowed with a nice boundary, so for instance, if we are talking about hyperbolic group, then one can ask whether this sequence of convolution powers converges in the corresponding hyperbolic multiplication. And the answer is yes. And this sequence of convolution powers converges to a limit boundary measure, which, since here we are talking about convolution powers, the boundary measure also has to be somehow invariant with respect to this convolution operator, and that's precisely the stationarity property which was evoked by Alex in the previous. Now, how does one prove this convergence? Actually, here, for proving this convergence, one would need another sequence of probability methods. So this sequence was deterministic. But instead of this, now one can look just at the sample path of our random walks, and one can establish the convergence of this sample path to random boundary points. So here we have a random sequence of elements in our group, a sample path of our random walk, and then one can show that, let's say in a hyperbolic group, almost every sample path converges to a boundary point, to a random boundary point. That's what was also mentioned by Alex. Okay, now if I want to look instead of convergence of points at the convergence of probability measures, then I can say the following. I have random sequences of probability measures on the group, which converge. Now they are measures, not points. They converge to the delta measure at the corresponding limit. Okay, so here actually now you see that we have two instances of, in a sense, both of them quite degenerate because they're really two extremes. So in one case, we have a deterministic sequence of measures. So there is nothing random here, which converge to a certain limit measure on the boundary. Okay, in the second situation, we have a sequence of random measures, but these random measures are really very, very degenerate. They just delta measures. And saying that these delta measures quickly converge to a boundary measure, which of course is also delta measure, just another way in disguise of saying that the corresponding sequence of elements converges to a boundary. Now, from this point of view, it is natural to ask the following question. Can one interpolate between these two situations? Can one build a family of random sequences, parameterized by a certain parameter, which would interpolate between these two cases? And this is precisely where a branching random walks come into play. So that's a second random ingredient in the mechanism which I'm going to describe. So the first random mechanism was our random walk, on which we need our state space, which is a group and a probability measure on the. That's random walk. That's I think everyone is more or less familiar. The second mechanism is the mechanism of branching random processes, or sometimes they're called Galton. I think we're still allowed to use these names, especially Galton. And this mechanism is maybe even older than random walks, is also very, very natural. It's very natural. So what is a branching Markov chain? It is determined, like a random walk, it is determined just by a single distribution, which is a probability measure on non-negative integers, which is a probability measure on non-negative integers. And then this process develops in the following way. So the state space of this process is non-negative integers, or maybe I should say positive, even positive integers. But to describe the transition probabilities, it's really not very convenient to talk in this terms. So what are the transition probabilities and what are we talking about? We start just in one point, so the initial distribution of our chain is delta measure sitting at 1. And then what we do is the following: we sample randomly from this distribution, which is called offspring distribution. We sample a certain random number of children of this parent, of this single parent. Okay, so this number is random, and then what we do is that then we subject each of these children to the same procedure. So for each of them, we sample independently of everything else a certain number of offspring. Well, in principle, this distribution, the support of this distribution may include 0, so that in this case, there may be some children which won't produce any offspring. However, for simplicity, I will actually assume that this doesn't happen, so that everyone produces at least one offspring. That's just technical simplicity. Okay, and then, well, they give us a certain number of offspring in the second generation, and then we repeat it again and again. So this is what is called Galton-Watson branching process. Now the mechanism which describes this process is very simple because here the parameter which describes this process is a probability measure on positive image. So it's like usual random walk for which we also need our step distribution, and then everything is described just by this step distribution. In this case, the description is also very lapidary, so we need only one measure, only one parameter. However, the way we use this measure is quite different. We use it in order to generate the corresponding infinite tree. It's infinite because I have assumed that we want to do the extinction. Yes.
When you say the state space is Z, how should I think about the Z being encoded in here?
Okay, so the state space is for the elements of our state space. The elements of our state space is just the number of members of our population.
Okay.
Okay, so then one can write down explicitly the corresponding transition probabilities in terms of certain conversions.
So we're just keeping track of the number of people in each generation. We're not keeping track of the geometric structure.
No, formally not. Okay, so this is n0 equal to 1, then n1 for this example will be equal to 4. That's for children, then we have 1, 2, 5, 6, 7, 11. 11 offspring in the second generation and so on and so forth. You are right. In principle, for certain purposes, it makes sense to keep more structure. To keep this geometric structure. Okay, so now, here in principle, one can also consider the situation when our branching is deterministic. So, for instance, if this offspring distribution is concentrated just on a single number, for instance, 2. In this case, we would, instead of a random tree, we would at each step just each individual will produce 2 offspring, and then we will obtain just a binary rooted tree. That's a particular example. Okay, so now how can one combine these 2 random mechanisms? Well, in principle, what one can do, one can actually first generate a random Galton-Watson tree, and then perform what is called tree indexed random walk. So what is a tree indexed random walk? So that's actually a very natural construction. That's very natural construction. So what is an ordinary random walk? We have integer array, which is our time. And then on each of the segments of this integer array, we choose randomly and independently of everything else an increment. Okay, and then we multiply these increments consecutively along the direction of time, and this will be our random check. Now, in precisely the same way, if we have a certain tree, random or deterministic, doesn't matter, then what we can do, we can assign randomly and independently an increment to each edge of this tree. Okay, so here, a certain subscript. So these H with unspecified subscripts are random increments chosen independently from the same distribution, from the same step distribution. Okay, and then what can one do? we still have the direction of time, although our time now is indexed by 3. And then we can multiply these increments consecutively along geodesic segments or geodesic rates in our tree. Okay, so in this way, in particular, if we fix a certain moment of time, let's say t, then here, the size of the population at the time t is precisely the size of the level, of the corresponding level with number t. And moreover, here at each vertex from this level, we will also have the corresponding position of our random walk, the corresponding product of the increments. Written in this way. Yeah.
Yeah, sorry, why wouldn't the elements of the HI, why wouldn't they be the vertices of HI?
Well, one could think about them as vertices, but you see, in this case, I would have to put a certain increment here at the root. So which means that there will be a common increment for all branches. So instead, well, it's just technically more convenient to really to make, because you see the H symbolizes a certain transition between two levels. And we add to this H, we also add information about what happens with the space coordinate while we transition from 0 to 1 in time. So it's more natural to assign increments to H's. Okay, so yeah, so now what one can do is, well, essentially, I have already described this random process, which consists in a combination of these two mechanisms: the Galton-Watson branching process, which is described by this parameter t, and my distribution of my random. Okay, one can actually go a little bit further, and it's quite natural. And instead, one can say the following, that we are given a measure, let me denote it by, let's say, M, like this. So that's a measure on finite configurations on the group. So, for instance, it can be something like this. Well, this finite configuration, so what is it? Well, I have my group, and I have a certain finite population on the group. And I also know where the members of this population are sitting. For example, 2 elements will be sitting at the identity of the group, and one will be sitting, let's say, elsewhere. Okay, so that's what probabilists like to call point measurement. Okay, and then my process is the following. So at time 0, I start just with the population which consists of 1 point sitting at the identity of the group. And then what I do, I just replace this identity particle sitting at the identity with a random configuration sample from this distribution. Okay, so this gives me my random population at time 1. And then I repeat the same independently with each of the members of my first generation, namely up to the appropriate shift by the group, because I want everything to be equivariant. I replace each element, or rather configuration segment, sitting at the delta configuration sitting at this element G, I replace it with G, let's say, kappa, where this kappa is sampled from the distribution. Okay, so that's a general branching process on a group. That's a general branching process on the group. Okay, so now what is now what's important for me is the corresponding branching number. So lambda is just the average number of, yeah, and of course I should have said that this model in particular contains the one which I described at the very beginning, when we just take independently the products of Galton-Watson branching and the usual random walk. Okay, then what I need, and what is very important for me, is the branching number of this process. So that's what just the average size of these populations. So M, this curly M, is a distribution on populations. And this is the number of elements in a population. Okay? So that's roughly speaking by how much our population is multiplied at every step. Okay, so now the question is the following. The question is the following. So now I have a sequence of population. So I start with the population keeping the identity of the group. Then I have population which I obtain at time one just by replacing the identity with random population sample from my distribution, and then I repeat it again and again. So I obtain a sequence of populations, and now one can consider these populations as discrete measures, as point measures on our group. Okay? And then the question is, of course, the masses of these measures, they will be growing exponentially with lambda, will be exponent lambda. So maybe here I can remind the property of Galton-Watson processes that if we take the size of our population at time t divided by lambda to the power k, then this limit almost surely exists. This converges to the number which is, let's say, denoted by W. Existence of this limit is just a trivial consequence of the Martingale convergence theorem. However, what is non-trivial here and what makes difference with the usual theory of random walk on groups, where one also has to use the Martingale convergence theorem, let's say for bounded harmonic functions, is that this Martingale a priori is not bounded. Okay, and therefore, although it converges, nothing prevents us in principle from the limit being identically zero. Okay, and therefore here the key condition is the uniform integrability of this Martingale, which is guaranteed by the L log L condition. So the distribution P has to satisfy the L log L condition, so which is a little bit stronger than existence of the first moment.
Please, this meant P is distribution where?
P is the distribution on integers. Okay, and I wanted to satisfy the not just the first moment. Well, I need first moment in order to talk about the branching number. But I need a little bit more. So I need that the sum of the k would be fine.
And it's P who defines the branch.
This distribution P defines branching in the classical situation. Now I consider slightly more general situation, but actually,
But the classical is particular history or classical?
okay, classical situation is when we don't have any group, we are talking just about branching on of particles. They don't move.
Yes.
Okay, and in this classical situation, one has to control the growth of the population in order to make sure that the martingale convergence is well, that the martingale is uniformly integrable.
Meaning you have expectation which is bounded or?
Okay, so here I have this statement, which is always a martingale. Martingale always
With the
converges.
martingale convergence theory, one needs bounded in the sense that expectation. is kind of, right?
Okay, so we have a martingale, which is a sequence of n. Then if this martingale is non-negative, then it always converges. Okay, but then there are two questions about the convergence. First, whether this convergence also occurs in L1, whether the expectations also converge. That's the first question. And the second question is whether this limit is positive. And for the situation of branching processes, there is this condition goes back to Levinson, but it is Keston and Skibum who proved that L-log condition is necessary and sufficient for first uniform integrability of the martingale, and second for the positivity of the loop. Now, what I do consider
By positivity of the limit, by positively of the limit, you also mean that the limit converges to sort of what you were expected to.
no, that the limit is positive almost everywhere. Okay. Okay, now here my model is more general because here I have evolution both in time and in space. Okay, but if I consider only evolution in time, then it will be just a certain Galton-Watson process, and I require this Galton-Watson process to satisfy the same L-log L condition. L-log L condition. Okay, and now the main result. The main result is the following. The main result is the following. So suppose that our group is endowed with a boundary. Now we are given a measure on the space of configuration. Then I have lambda, which is the average branching number, which is over here. Yeah, it should be greater than 1. And then I also have the associated probability measure on the group, because indeed, I have a measure on configurations. Those configurations, I can also consider them as measures on our group. Okay, so therefore, if I average, then it will give me a certain measure on the group whose total mass will be equal to precisely this branching number lambda. Okay, and therefore, I will have also a certain probability measure on the group. To notice, let's take. Okay, so I take the image of my measure on the space of configurations. It was defined on the space of configuration, and then I obtain the corresponding measure on the group. So which is denoted like this, and then I have to divide by its total mass, which is precisely the branching number, and this will give me a probability measure on the group. Okay, now, what are the assumptions? So the assumptions are the following. I need the L log L.
Sorry, can I?
Yes.
I got lost. So what is the measure? Do you multiply the elements of the configuration together or?
No. I just, okay, so I have a configuration, right? Now configuration is just an integer valued measure on the group. Okay, and then what I do, I take the resulting integer valued measure on the group and I average them with the weights assigned to the configurations, which give me a certain measure on the group, which is not a probability measure, it's mass is equal precisely to this branching number. And if I divide by this branching number, then this will give me a measure on the group. So in particular, if I consider the first example which I gave, when we have independent branching driven by a Galton-Watson process and random walk on the group given by a certain step distribution, then I recover precisely this measure, which is the step distribution of my original result.
Yeah, sorry, I'm just
Yeah.
it's mixed a little bit.
Uh-huh.
A configuration, let's suppose you have a configuration of 2 points, right?
Yes.
So this to me is a measure on G cross B.
No. Configuration is always a measure on the group. Because what is a configuration? Configuration tells me for each element of the group, how many points sit in this point. This group element, right? Yes, or what is the configuration? There are 2 points sitting here and 1 point sitting there. So which means that I have 2 delta masses at this point and 1 delta mass here. And altogether I have a measure of total mass 3 sitting on this. And then I just average all these measures. Okay? The result is a certain measure with mass greater than 1. If I divide by its total mass, this will give me a probability. Okay, so now what are my assumptions? So first I need L condition on branching. And from the underlying measure on the group, I need the following, that the Dirichlet problem for the corresponding random walk on the group is solvable. So what does it mean? Boundary is solvable. What does it mean? It means the following. First of all, the random the sample path of my random walk, they converge to the boundary almost surely. And second, which is precisely the solvability of the Dirichlet problem, is the following. If I have a sequence of group elements Gn which converge to a certain boundary point, then the sequence of the corresponding delta measure, not delta measures, then the sequence of the corresponding harmonic measures converges to the delta measure at the point gamma. That's solvability of the Dirichlet problem. In classical terms, it means that if you have a continuous function on the boundary, then it can be harmonically extended inside our space. But actually, it means precisely this. It's a combination of two facts. First one is boundary convergence, and second, the weak continuity of the resulting harmonic measures. That's solvability of the Dirichlet problem. And it's satisfied in many situations, for instance, once again, for our beloved hyperbolic groups with arbitrary step distribution. Okay, and now these are the conditions, and now the result under this condition is what one would expect. So, and this is, I forgot to say, this is a joint work with Wolfgang Wurz. So under these conditions, if we take a random population at time n, so once again, this population, as any population, can be considered as an integer valued measure on our group. Now, the mass of this measure is precisely the number of points in the nth generation. And then we know by the classical Galton-Watson theorem, by Kestenstiegel or Levinson theorem, that we have to normalize by the nth power of lambda n. Okay, so then if I look at the mass of this measure divided by lambda n, then the Kestenstiegel theorem tells us that this number converges to a certain positive limit. Okay, now I'm not passing to masses. Now I'm talking just about these measures normalized by the division by lambda n. And the claim is that these measures on our group, they converge to random measures and infinity on the boundary.
And it is a measure corresponding to nth population also.
Okay, so once again, so we run our branching random walk. So we start from a single particle at the identity of the group. We let it multiply, produce a certain number of offspring, which also move in certain directions inside the group. Okay, we repeat it n times, applying these mechanisms independently to each of the particles. At time n, we have a certain random population on the group.
And there is a distribution, right?
A certain collection of points. Okay,
And a probability measure, no?
no, it's not probability measure. It's an integer value measure. So that's the sum of delta measures sitting at each point of the population.
But each point is random.
Well, the whole population is random, yes. So at time 10, for instance, we obtain 1 million particles sitting in various places on our.
And n is the distribution. And then it's not the number of points, right?
And n is the population, the measure, the integer, the occupation measure, if you
The
will.
occupation measure at time n, right?
At time n, random occupation measure at time n.
Now it's like a strengthening and the version, right? So you say usual theorem is just about branch process, right? About.
The usual theorem is just about the number of points,
And
about the
can
total
the
time.
usual one, can we consider as a very particular case of your result? Or not?
Yes, if our group consists just, if our group is trivial, consists just of one element, yeah, then it will be
Yes,
particular.
so this is
Yeah.
general statement, but in particular, the very
Yeah.
particular result having.
Yes, yes, yeah.
This M infinity isn't fixed. So it's.
No, that's a random measure. That's,
Is it important that points don't die?
not really, not really. So here it's just a technical assumption, because, which simplifies life. Because, otherwise, what may happen is the following. So suppose that you are allowed to produce no offspring with some probability. Then it just means that with certain non-zero probability, eventually this whole population will extinct. Okay, and the typical trick in this branching process theory is to condition by non-extinction. And then conditioning by non-extinction actually leads to another branching process with by offspring distribution. So it's really pure technicality. Okay, so now I'm claiming that this setup can indeed be considered as an interpolation, which was my goal, as an interpolation between the, on one hand, deterministic sequence of convolutions, and on the other hand, the convergence of individual sample paths. Well, indeed, if lambda is equal to 1, which means that there is no branching, then here actually our populations consist just of a single point at any time. So we only have displacement, but there is no branching. And in this case, we obtain precisely the convergence of sample path or the associated delta measure. Now, what happens when lambda is getting bigger and bigger? So that's convergence of now, if lambda goes to infinity, then what happens is that we may think that at each point we will have a lot of particles. At each point we will have a lot of particles because lambda is very high, and therefore our population really saturates the group. And then if at the same position we have a lot of particles, then by the law of large numbers, if we do independent branching at this point, this is essentially the same as applying the average of those branching measures to the delta measure at this point. So in this situation, we will really be dealing, instead of this random sequence n, in the limit we will be dealing just with the sequence of n-fold convolution powers. Okay, so this is indeed an interpolation family. And well, one can actually reformulate this result in a slightly different form. So here, as we know, if you look at the size of the populations, we normalize by these powers of the branching number, and we know that the limit is a certain number which is non-zero. That's the second part of the Kestenstiegel theorem. And therefore, instead of this, one could consider normalization just like this. Just by the size of our population. So at time n, we have a certain random population, which we consider as an integer valued measure. If we divide this measure by the total mass, this is just a probability measure. That's what probabilists call empirical distribution of our sample, of our random population. And then this result implies that the empirical distributions of our random populations converge to limit measure, converge to limit measure. So, that's, the main result. And, it's actually quite, it was quite surprising for us that, this, problem wasn't formulated, in this way, although branching random walks, they were, considered earlier, but for some reason, and that's actually a phenomenon quite typical for the probabilistic community. They kind of tire of dealing with matter. Instead, they prefer excursions to the topological world. So questions like this, they were asked in the topological setup. For instance, well, we have sequence of populations. We'll look at the support of these populations. What can one say about the limits of these supports? But in my opinion, as always, in probabilistic setups, one should first ask questions of mere theoretical nature, and maybe only after that foray into topology. Now, what are the questions here? And the questions are manifold because, well, there is a lot of results about the convergence of convolution powers and about the convergence of sample paths. And now, essentially, whatever one can interpolate between these questions will provide a meaningful question in this situation. So, for instance, in the setup of hyperbolic groups, there is a well-known relation between the rate of escape, the entropy, and the Hausdorff dimension of the harmonic measure. Okay, so this holds for, so who is the harmonic measure? The harmonic measure is the limit of convolution power. If we look at the other end of the spectrum, if we look at the convergence of sample paths, then there is nothing to say about the Hausdorff dimension because the limit measures are just delta measures. Now, what happens in between along this interpolation family? Here, actually, even the existence of these constants, which are the rate of escape and the asymptotic entropy, is not obvious for the families of random measures which arise in this situation. The reason is that it is not, at least for the time, it is not obvious how to combine two main ideas which are used in the classical setup. So what are these ideas? Is that one looks at certain invariants. These invariants are subadditive, and then one applies subadditive ergodic theorem. Question. The question, how does one combine subadditivity with branching? It's not known yet.
So you mean there is no particular question, or there is some question?
No, well, there is a lot of questions. So the first question is the following. Okay, so I have this sequence of measures, and n divided by the size of the population, which is a random probability measure. And now I just take the first moment of these measures, of these random measures. And then I divide it by n. I divide it by n, and I ask whether there exists a limit. Well, if it exists, most likely it will be the same at the rate of escape of our original random walk, but for the time being, we don't know whether it exists. Yes.
So, I guess you can ask us both about the renormalized version and the non-renormalized version, so the empirical measure and the branching processing. Do they converge to the hitting measures of some random walk on hyperbolic? It seems like they really should for the non-renormalizing, but I have no idea.
That's a very good question. I don't, at the moment, I don't see how they would. Okay, so you are asking whether these limit measures, which were, let's say here.
Take the expectation.
Well, these ones are not normalized, but
Take the expectation.
no, if I take the expectation, then of course this expectation, I forgot to mention this expectation, of course, will be the harmonic measure of the underlying random.
Sure, but I take the expectation of the last one.
Which one?
infinity. If you converge to infinity.
Oh, this one?
Yeah.
Yeah, the expectation is precisely the harmonic measure of the random walk driven by, where is my measure? Driven by the measure mu.
Sure, which I guess makes sense for you, like, it's a some sort of Mario convergence type thing. What about the empirical version? Is it true there?
Empirical ones, you see, in a sense, to average, the empirical ones would violate the nature. Would violate the nature. One could really average them with the corresponding weights.
It's easy to try to converge to the.
Huh?
So you don't think?
Okay, so they may converge, but somehow that's not what one should consider, in my opinion.
One of the questions, what about groups which are not large, where we don't have kind of the usual boundary? Or what about the important groups and?
Well,
Is there
on the
something-
important groups, because here you see what we are obtaining. We obtain this family of measures, they are random measures, and the expectation, the average of these random measures is the harmonic measure of our ordinary random walk.
Yes.
Okay, so if this harmonic measure is trivial,
Yeah, okay,
Then
these questions,
all
yes,
these
but
ones are-
there are some other interesting questions to ask
Yeah,
to your branching random box. I think in your paper, I've read, you have some question I haven't quite understood, and you mentioned it for the.
well, one can ask a lot of questions, for instance, about the measure classes of these measures. So here I would expect that if the parameter lambda is big enough, then these measures will actually be equivalent to the harmonic measure class. For instance, unfortunately, here there are too many questions and no answer. for the time
But there are many apparently very difficult questions, right? Like in your result, when sort of a very far-going generalization of some observations for usual random box, and it can happen for branch random box. But I wonder, are there maybe some completely new phenomena that happen for the branching works? Is there, on the level of the question, something we can ask that for some particular groups would expect very different for random
Well,
box and for branch
you
random?
see here, what is new is really that one obtained this interpolation family between delta measures and kind of full support harmonic measures. And they're actually from purely geometric measure theory point of view, it's quite interesting to understand. For instance, if we're talking just about the free group. So from the point of view of geometric measure theory, it's a totally trivial object. But who are those measures with, I'm sure they will have intermediate Hauser dimension. How are they organized? What are these measures of intermediate Hauser dimension on the boundary of free group? Yeah, maybe I should mention that actually parallel with our work, there was another group also consisting just of two people, Elisabetta Candelero and Tom Hashcroft, who proved a very similar result, but in a different setup. Namely, they proved analogous convergence. They only considered the model of independent displacement and branching, but also the topological setup is quite different. They have proved it for the Martin boundary. And it's quite different because on one hand, Martin boundary doesn't necessarily have to have the Dirichlet problem solvable. So in this point, this more from this point of view, it's more general. On the other hand, well, to know what the Martin boundary is, except for well, very known set of situations. Yes.
Isn't stochastic cellular automata a similar concept?
Stochastic.
Still, arbitrary cellular automata like live game, yeah, where configurations evolve. And there is some generalization, I don't know exact definition, but that uses probability. It looks like something similar to this.
Well, it's, well, those stellar automata, they are more complicated because here what happens is that
Here,
each particle branches in the, they don't interfere. Whereas for those stellar automata, the transition probabilities really depend on configurations in non-trivial way, but yeah, that's also a reasonable question, but more general one. General.
We forgot to thank the speaker,
Ah.
we have many other questions, I don't know.
Is there,
Now,
is there any question? Is there any question for M infinity? I mean, like Mandelbrot cascade. I mean, it's,
For L infinity,
M infinity. Do you have a functional equation? I mean, a stationary equation.
for the measures themselves or for the weight?
For the M infinity, I mean, it really looks like a Mandelbrot cascade. It's
Like stationarity, that's a very good question. Most likely, yes, well, as you have guessed, but we didn't think about that yet, but now we will.
okay.
Here's some not very serious question, but inspired by your comment about group of researchers and the group consists of two persons. I wonder, so usual branching process, right? And so you also, you have branching, so you branch, that's a quickly growing population. Is there some sense in a very slowly branching process, so that each time you walk and only very, very you branch, so that not to have many, many particles, but rather very small groups of particles?
Well, you see what you are asking about, you want to make the, okay, so here we have two mechanisms, branching and displacement.
Yes.
And you want to make their relationship more complicated.
Not really more big, so maybe I want to make the random walk part, the displacement part more stronger, so that the branch is very, very big. So something that resembles one particle, but only rarely branch, no?
Yeah, but look, either it's like in those jokes, it's either you have it or you don't. So either you don't have any branching or you do have branching.
But it could be a bit different behavior because if it happens everywhere, right? There is
Yes.
the same mechanism of convergence, right? Much more
Well,
complicated, but
then, you see, then you have to sacrifice space homogeneity.
it is complicated.
Yeah, maybe one more argument in my apology, which I wanted to mention, but I forgot. So this is, once again, it's not that exotic because, for instance, even if you look just at ordinary random walks, then, well, one can consider the J-kernel, and then one can also consider the so-called lambda green kernel with what's it called in operator here, resolvent. And this lambda green kernel actually is precisely the expectation of the occupation measures which arise for branching random walk with parameter lambda. Then this is lambda green kernel. So once again, it's not that far from the usual world.
The small question, how much, so for you, it's a discrete context, right? So can the, or not only?
Discrete for what? For time or for
No,
space?
for the space.
Doesn't really.
Or you have maybe general statements, so.
Well, there are actually. Well, there is a very well established area of so-called super. If I'm not mistaken, they're called super branching processes, and that's diffusion processes on in the continuous sense when we are talking about populations which are described by densities, not by occupation about populations which are continuous, which are not discrete. And there,
But I simply meant maybe it's covered if this sort of an interesting question, but I meant simply if the space is continuous without population.
if the space is continuous, I don't think it would make much difference, because I don't think it would make much difference because the methods are actually quite soft. So we are, what do we use? We use, well, this custom or Levinson-Keston-Stigum theorem. That's for plane branching process, and then we use just the probability of the Dirichlet problem. So it's very, very soft.
So it could be a Brownian model somewhere simply branching.
It could be, but then, yeah, if you want to indulge in those models, yeah, one can do it, yes.
You mentioned hyperbolic right quantum state and hyperbolic manifold, right?
Yeah, in principle, yes. Because for us, actually, but once again, since this is a group theory seminar, so I was only talking about the group invariant key, but actually, in my opinion, the most interesting part of our work is that it doesn't require any group invariance, and it is applicable actually to any branching processes. The only condition is the existence of this branching number, so that it will be the same at every point. But otherwise, no space homogeneity is required.
And so far, you don't have some specific observation, like the usual random oxide, there is so many things so different in the homogeneous state, like your entropy criterion, many other things, like here you don't have.
Well, you see, once again, what I present here is just, in a sense, the first result in this hopefully future theory, namely that's the existence of these boundary measures. And then, of course, if we want to study their properties in more detail, then here, of course, the space homogeneity will become instrumental.
That might be not on instrumental, on the level of formulation, right? So, you know, entropy criterion doesn't talk all.
But look, let's once again look at our beloved hyperbolic groups. Okay, then the boundary convergence can also be established if we have a general hyperbolic graph with any.
Yes, but some other state.
Yeah, so that there exist harmonic measures, and well, the Dirichlet problem is always solvable for an arbitrary hyperbolic graph. Well, presuming that it is non-amenable. But of course, if you want to say something meaningful about harmonic measures, then you have to impose some homogeneity assumptions. So here, once again, I only show the existence of this limit boundary measure. But if you want to obtain finer information about them, then you have to ask for more.
Any other questions or comments? If not, let's thank the speaker.
Okay.
We have a tea break, so tea and coffee is in the kitchen, although the rest is here. And coffee.